Today we would like to present to you about horizontal well testing. So this is our group member according to the presentation list.
Hi, my name is Shahidi 18321. First of all, let us get to know the definition of horizontal well testing. Based on my understanding, horizontal well testing is a test that is conducted on a well that is parallel to reservoir bedding. Then, we can use the useful data from this test to evaluate and enhancing well performance. Next, we move on to my second point, which is the advantages of horizontal well over vertical well. The first point is by using horizontal well, large volume of reservoir can be drained. This is because technically horizontal well has greater contact with given length of reservoir than a vertical well. Besides that, with horizontal well, there will be higher production even from thin pay zone compared to vertical well. The main reason is that a conventional well will intersect a relatively thin section of reservoir, but for horizontal well, it can run along the length of reservoir and therefore producing much more hydrocarbon. Furthermore, the horizontal well also able to minimize water and gas zoning problem because of the lower pressure drawdown. We also can use horizontal well in order to reduce near wellbore gas velocities as well as turbulence. Besides that, a long horizontal well has the ability to provide higher injectivity rates in secondary and enhanced or recovery applications, therefore increasing the production from the well. And lastly, the length of horizontal well can provide contact with multiple fractions along the perforation zones, and it will greatly improve productivity. This particular situation happens because horizontal well has a much greater chance of intersecting vertical or steeply dipping natural fractures compared to conventional well.
Thanks for the detailed explanation from Shahidi. I'm Lai Chun Xiang, ID 18158. We will continue the next part of horizontal well drilling, which is the flow regime. The first flow regime to be seen is the early time radial flow. In this period, the presence of the upper and lower boundaries are not being felt in the wellbore. This results the well to act like an infinite medium. The axis of the flow is radial in this early time, but bear in mind that if there is a large difference between vertical and horizontal permeability, then this will cause the flow to be elliptical and not circular. On the other hand, if the vertical over horizontal permeability is small, early radial flow will not be seen. The second flow regime is the intermediate time radial flow. In this period, the top and bottom boundaries exert their influences, while the horizontal well length is still important. Early linear flow is when both vertical boundaries are encountered. In some other cases, intermediate time radial will occur if the well is located close to either one of the boundary and known as hemi-radial flow. This is a linear flow regime, and in some occasions, linear flow will not occur when formation is thick and kV over kH is small. At late time, the influence of the upper and lower boundaries will cause another radial flow regime where the axis of the flow is vertical, but the flow is still radial in the horizontal plane. Eventually, flow will begin to come into the wellbore from beyond the end of the well and is named as late pseudoradial. The flow regime will then continue until the area affected by the production reaches one of the sides of the reservoir. Once the area affected is and the entire width of the reservoir, we will have a linear flow regime known as late linear flow regime. Remember, all the flow will not occur if other external boundaries are felt first, and will definitely not occur if the pressure is supported by an aquifer or gas cap.
My name is Nur Afika 18204 and I will further explain to you about pressure behavior of horizontal wells. Okay, first you need to plot a log-log graph of the normalized pressure versus the pressure derivative. Plot the log-log graph of the normalized pressure and the pressure derivative versus line. So as you can see here, the solid line represents the normalized pressure graph and the dotted line represents the pressure derivative graph. Okay, so for the first section of this graph, it represents the early time pseudo-radial flow and effective permeability yields square root Ky Kz. For the second section, it represents the intermediate time linear flow. Since the slope is half of the pressure derivative graph, so it gives the effective permeability of Ky. For the last section of the graph, it represents the late time pseudo-radial flow. Okay, so for this section, you can see the effective permeability is square root Kx Ky. Okay, for the wellbore storage is more prominent in horizontal than vertical well testing because more fluids exist in the wellbore below the tools. It can mask the early time pseudo-radial flow, particularly if downhole flow rates are not available to account for it. Alright, from the same graph, we can determine the duration of wellbore storage, the magnitude of the wellbore storage, the estimation of vertical permeability, the effective length of horizontal well, and lastly, the estimation of horizontal permeability and the reservoir pressure. So that's all for the pressure behavior of horizontal well graph. Thank you.
There are some various parameters that are needed attention in testing the horizontal well, including the first one is initial reservoir pressure, noted as PI, mechanical skin or true skin, noted as S, permeability thickness, K times with H, perforated wellbore line, noted as HW, permeability, noted as K, and horizontal distance between wellbore to the bottom of the formation, that's sec W. Also, there are various kinds of pressure tests that can be determined from horizontal well testing. These include the first one is drawdown test, build-up test, interference test, pulse test, and drill stem test. But we'll only be looking into a drawdown test for this one particular chapter. For early radial flow, also known as vertical flow, permeability is only counted at y and z plane, as shown in the diagram, where Ky is known as Kh and Kz is known as Kv. Drawdown can be further determined by using the equation as stated, and from this equation, true skin can be determined. For intermediate time linear flows, the second phase, permeability is only counted at y-axis plane. As stated in the diagram, Ky is known as Kh. Drawdown can be further determined by using the equation as stated, and skin then can be calculated from the equation. The last phase, which is the late horizontal radial flow, permeability is only counted at x and y plane, where Ky is equal to Kh and Kx is Kx. The drawdown can then be determined by the equation Pi minus Pwf equals to as noted, and then from the equation, skin can also be determined.
Thank you, Shafiq, for that brilliant explanation. My name is Teki, ID 18431, and today I'm going to explain about the drainage area of horizontal wells, which are different from vertical wells. Okay, now let's take a look at the diagram. You can see that in the top view of the drainage area is a rectangle of length L, and each end of the horizontal well is represented by a vertical well that drains an area of a semicircle with radius B. A horizontal well can be looked upon as a number of vertical wells drilling together next to each other. Joshi 1991 proposed two methods for calculating the drainage area of a horizontal well. In method 1, Joshi proposed that the drainage area is represented by two semicircles of radius B, which is equivalent to a radius of a vertical well, REV. The rectangle has dimensions of L times 2B, where B is the radius of the semicircle. Therefore, it is represented in the following formula, where A equals to length times 2B which is the area of the semicircle, plus the area of the two semicircles, which combines into a circle. And this is the formula of the circle, pi b squared. And all this is divided by a conversion factor into feet squared, which is 43560. So L times 2b is this, and pi b squared is the area, which is combined by two semicircles. In method 2, Joshi assumed that the horizontal well drainage area is an ellipse, given by A equals to pi times A divided by, given by A equals to pi times A times B divided by 43560, which is the conversion factor, with A being L over 2 plus B, which is also the half major axis of an ellipse. Joshi also noted that both methods give different values for the drainage area, and suggested assigning the average value for drainage area of the horizontal well, which is by adding the two values and dividing by 2, which means method 1 and method 2 add together and divided by 2. Most of the production rate equations require the value of the drainage area of the horizontal well, which is given by this following formula. So it's worth taking note to memorize this formula, I hope. Okay, now let's take a look at a simple exercise on drainage radius, which may or may not be covered in our syllabus, but it's still worth taking note anyway. Okay, now we can see that from this question, the total area to be leased is 480 acres, with each vertical well were to drain 40 acres, and there are 12 vertical wells. We have to find how many horizontal wells that are 1000 feet long and how many horizontal wells that are 2000 feet long, which make up a total of 12 wells. The first step will be to calculate the drainage area of the vertical well, which is using the REV formula. The area of the vertical well, which is 40, which is given a question, times the conversion factor divided by pi equals to 745. Note that REV equals to B, which is the radius of the semicircle at the end of the horizontal well. After finding REV, we have to calculate the drainage area of the 1000 and 2000 feet long horizontal wells using Joshi's two methods, which is the rectangle plus two semicircles and the ellipse method. Okay, now in method 1, we plug in the values of B, which is R equivalent, and obtain A. So B, as you can see here, this is 745, B 745, L 1000, and blah blah blah, we get 74 acres. We do the same thing for the 2000 feet horizontal well, and we obtain two areas. In method 2, we plug in the values of B and obtain A from method 2 for 1000 feet wells and 2000 feet wells. I remember A is the major axis of the ellipse. Remember that both methods give different values. Therefore, we have to take the average of both values for 1000 feet and 2000 feet respectively. And then we calculate the number of horizontal wells for 1000 feet and 2000 feet by taking the total area, which is the area to be leased, 480, divided by the drainage area, which is the area calculated. So let's see, drainage area per well. After we take the average, 71 divided 480 divided by 71, we get 7, and 480 divided by 101, we get 5. So these two should add up to 12, which is correct. Remember, we have to divide the total area to be leased into 12 wells. Now let's take a look at estimating the horizontal well productivity. So now let's take a look at these two familiar graphs. Like what we learned in Dr. Huck's tuner's class, we can see that the graph is divided into ETR, MTR, and LTR. After the transient period ends, which is the unsteady state flow, the pseudo steady state flow starts, or maybe the steady state flow can start again somehow. Alright, so we have a storage, transition. Okay, we all know this. Okay, we all know what steady state means, which is the pressure at any point does not change with time. There are several methods to predict the PI for horizontal wells. These include the Bosirov method, the Geiger, Rees, and Jordan method, the Renard and Dupuy method, and the Joshi method. The methods are the following. Whereas all this, which is I'm going to just go into brief because it's not really covered in our syllabus. But let's take a look at isotropic. What isotropic means? An isotropic reservoir means that the physical property, which in this case is permeability, has the same value measured in different directions, where an isotropic means that the physical property has different values when measured in different directions. So when you measure at different directions, we will get a different K. Therefore, all these smart people have divided the method into two, which is calculating for isotropic and calculating for anisotropic. So let's briefly just look at all the equations. Blah blah blah. Okay, now let's take a look for the horizontal well productivity under semi-steady state flow. Simple methods in this semi-steady state flow, like Vogel, cannot be used to construct the IPR of horizontal wells. Therefore, the following methods are used to calculate PI for horizontal wells under semi-steady state flow. It's the Bernard-Kayla and Aziz. Bernard-Kayla and Aziz used a reservoir model to generate IPRs for a number of wells and found that a combination of Vogel and Fekowicz method would fit the generated data. Cheng presented a form of Vogel equation for horizontal wells that is based from a numerical simulator, and Petlanto and Economides developed a generalized IPR equation for horizontal wells and multilateral wells. Oops, finished already. Okay, so let's take a look. Let's take a recap back in what we learned in my part. First, we learned about the two methods in calculating the drainage area, where the first one is L times 2B, is the area of the rectangle, plus pi times B squared, which is the two semicircles combined into a circle. Where the second method, where Joshi assumed that the drainage area is represented by an ellipse, and given by A equals to pi times A times B, when A equals to L over 2 plus B, which is L over 2 plus B over here, where A is our major axis, blah blah blah. Alright, and we need to note this formula to calculate the drainage radius exercise, where we will use that formula to get B. So we calculate for both wells. We need to take the average because both methods give different values. So after getting the average, finding the number of wells, alright, we learn the methods in estimating horizontal well productivity, which are all these people. And we have taken a look at how to estimate horizontal well productivity, which is by all these equations, which are not coming out in finals. Thank you.